I am delighted to welcome our next speaker onto stage for us. He is the Staff Engineering Manager at GitHub, here to speak to us today about CodeQL. Can I introduce and can we give an amazing Codegarden welcome to Jonas Jensen.
Thanks a lot. Thanks everybody for the warm welcome. I'm here to speak about my favorite topic in the whole world, which is CodeQL. I'm glad I have a microphone because I'm recovering from a cold and my voice is not quite there yet. But I hope it'll last for 13 minutes. CodeQL is a platform for analyzing source code, and it's especially good at finding security-related bugs. And in this talk, I'm going to show you how to apply that practically in an Umbraco context. And then I'm going to dive a bit deeper and tell you how it all works and how you can kind of see CodeQL as a way to get a perspective on databases, on static analysis, and on programming languages in general by seeing this very specifically tailored system and what we gain from that. But let's first dive into some examples of how this applies to Umbraco packages. So I took two of the most popular packages on the Umbraco marketplace and ran CodeQL on them with the kind of default setup to see are there any interesting security bugs that we could talk about. And this is not to pick on anyone or any packages in particular, but I wanted to also look at Umbraco itself, but it turns out Umbraco already uses CodeQL, so they've shaken out all the interesting bugs. So here's what it looks like when you run CodeQL through GitHub code scanning. It's free for open source, anyone can do that. And here's an alert. The type of problem here is an XPath injection. So what you can maybe see here is that if the prefix variable contains a single quote, then it escapes out of the surrounding XPath query and can really execute any kind of XPath. So it should have been escaped or processed in some other way. So this is an alert that CodeQL has found, which also means it has determined that there was no escaping or insufficient escaping happening here. And it has determined that the prefix variable here comes all the way from user-controlled or attacker-controlled input. And if we click the little link to see what is the user-provided value that it has found, then we are taken to the HTTP post handler where prefix comes in, and then it goes through like all sorts of calls across all sorts of functions and ends up there at the XPath injection. So that's one example. Just to show you more of a range of examples, here's another potential problem. It's a vulnerability class called zipslip. What happens is when you extract a zip file, the contents of that zip file will be file names, relative paths, and they may have ... in their relative path name. So if you just take the path names out of a zip file and then like say I want to extract it to this path and it has ... then it can go anywhere in the file system. And so whenever you programmatically extract a zip file, you have to check for ... or use a library that does that. And here CodeQL has determined, well, what's highlighted here is the place where we take the full name of a file out of a zip file, the relative path. And then if we click to see what is the file system operation that it's talking about, we see that here a variable called destination is extracted. And CodeQL has checked everything in between that there is no attempt to avoid the ... Final example here is another injection type of vulnerability, a log injection. So whenever you log something that can be user-controlled like this and just plain concatenate it with the log message, then in principle, that if that can contain anything like new lines, for example, then an attacker can append a number of lines to your log file, and they look just like legitimate log file entries, but they are not. So before putting anything in a log file, it's also a good idea to sanitize it and make sure it cannot contain new lines and such. And here is the evidence of where the file variable came from. All right. So I showed you kind of the beginning and end. We call that the source and the sink in a Taint tracking problem. But CodeQL will also show you everything in between. So if you have better eyesight than I have, then you can see a little snippet that I took out of a very long path from one of the log injections. The full path has 48 steps in total, and it goes across 5 files. The data goes into collections and back out. It goes into lambdas via variable captures. The calls pass through virtual dispatch and so on. And CodeQL tracks it all the way through with its whole program Taint tracking analysis. So just to summarize all that, if you are maintaining any kind of open source package, then you should be interested in what security issues might there be in there. If you are crucially depending on any sort of open source package, which we all do, then you should be equally interested. And CodeQL is a very capable tool for finding these problems. And what you saw here is when we put all the things together. So now I'm going to take them apart and look at the individual components that go into this. So first of all, we have like, the whole engine that runs everything. I like this picture. It looks sort of like a robotic head, maybe, or a mechanical machine. The way CodeQL works is essentially by turning your source code into a database and running queries against that. Very sophisticated queries. So up at the top, we take the source code of your program and we run it through what we call an extractor, which is a language-specific component that turns it into a database with also a language-specific database schema. So in this case, I was looking at C#. And then on the left, what also goes into the database engine is the queries. We have a standard set of queries, for example, for these injection type of vulnerabilities. And these queries share a lot of libraries. So often the queries are quite simple, and they instantiate shared libraries in some way. And the libraries can be language dependent, or they can be language independent. And then then we have a database engine. It's a custom database engine that can then interpret all these libraries and queries. And in the case of a taint tracking analysis, that breaks down to first enumerating what are all the potential sources of taint. That will usually be all data that comes into an HTTP handler. And then it enumerates all the sinks to a specific query. So that could, for example, be an XPath expression that is executed somewhere. And then the data flow library connects all that and tries to connect sources to sinks by looking at how does data flow around the program. Is it escaped anywhere so the flow is cut off, or is it like concatenated, for example, so that it remains tainted? So let's have a look at what a query looks like. So all our analysis is written in this custom programming language that we call QL, just for query language. And this is an example of a very basic query, just a few lines. But the first line is to import the Java library. So this is to analyze some Java code. And what this query is looking for is the code pattern you see on the left. So there is an if statement with an empty then block. So maybe that's a mistake. For some reason, we're trying to look for that. And a QL query is a declarative thing. Sometimes it looks like an SQL query, like in this case, or a link query, if you like. So when we import the Java library, then we get classes like if statement and block, and then we can declaratively specify what is it we're looking for in the database. We're looking for combinations of an if statement and a block, where the block is the then case of the if statement, and where the block number of statements is 0. And when we, for all blocks we find like that, we want to select the block and we want to select an alert message. And that can then all go through and get presented as like the alerts we just saw. So the interesting parts here are that this is declarative. We're just saying what does the thing look like that we're trying to find. And then it goes through a query optimizer that will find the best strategy for executing this query. And here is my guess at how this query will probably be executed. And I won't read everything off the slide, but I want to talk about what the building blocks are here. So everything is about relations, like in a database. So all the data is in relations, and what we can do with a relation is we can create them, we can join them, like database joins, and we can subtract them from each other. Those are the building blocks we put together, and then the query optimizer takes it from there. In step 1, the idea is all the indexes that we will need later are created on the fly. So it's a database, but you don't have to worry about creating indexes. And then in step 2, we find all the blocks that are not empty. And then in step 3, we subtract that from all the blocks. And that leaves us with all the blocks that are empty. And this is maybe a bit of a funny execution strategy, and there could be other strategies that work, but this works well enough, and as a user, you don't have to think about that. Just to show a bit more advanced QL, I've taken some snippets from the zip-slip query we saw earlier. So at the top, we see programmatically what it looks like. The source of Taint, in this case, is the place where we take the full name out of a zip archive entry. And we describe that as well, we want any property access where the target has that full name. One thing to sort of notice here is that, well, it looks like, these things look like method calls, but they go both ways. So it's not like we are necessarily looking at a property access and then asking what is its full name. In this case, the computation actually happens in reverse. So we're looking at a bunch of full names and finding the property accesses that match. And then we see down below we're instantiating a module. So here we're instantiating a shared library to configure the Taint tracking module. And finally, we have a from-where select kind of query like we saw previously. In the same style, you select the elements of the program you want to highlight, and you give an error message. Here it's a little bit more sophisticated, and there's a little bit more going on in order to set it up so that the path from source to sink will show up. But it's the same essential idea. So that's a little taste of what this looks like in practice. And now we're going to take one step deeper and talk about recursion, because this is really where the magic happens. So far we've seen non-recursive queries like you're used to in SQL, but the real power of QL, which is a dialect of data log, if you've heard about that, is recursive queries. And the hello world example of a recursive query looks like this. It's a reachability predicate. And the good thing here is the hello world example of recursion in these languages also just happens to be pretty much how the Taint tracking library works, because Taint tracking is all about reachability. So it's a simplified version of that, you could say. So assume you have a relation called start and a relation called step. Then you want to find out, well, what are all the x's that can be reached. So here we declaratively say that an x can be reached if it's in the start set, or if there is a y that can be reached. Is it not showing what I'm seeing? Okay, then I'm... Okay, but now we went too far ahead. Okay, one back. I hope you've been seeing the slides I've been seeing all along. Okay, so an x can be reached if it is in the start set, or if there is a y that can be reached, and we can step from y to x. That is the idea. And this is a declarative way to describe what we want to see, but it's not a very good recipe for actually executing this. You could naively try to execute this by essentially iterating it, but then you would be computing the same thing over and over again, so we don't want that. But there is a standard way to transform this into something that can be executed efficiently. And let me show you how that looks here. So we do this by iteration, where we say we compute the sets of what can be reached in I steps. So what can be reached in 0 steps, that's everything in the start. And then what can be reached in I+1 steps, well, that's everything where there exists something that could be reached in exactly I steps, and you can step from that to your new x. So the point here is you're just looking at what could be reached in exactly I steps. So that's a much smaller set than what could be overall previously reached at all. And then crucially, we subtract everything we've seen before, because that means we will eventually terminate. We will eventually have seen enough or have seen everything. And so we terminate this iteration when we come to an iteration when nothing more is discovered, nothing more new is discovered. So this is a sort of a standard transformation. And the CodeQL compiler will do this transformation for you. And in this very simple example, well, it was not a lot of effort to do this manually, but in more general cases, there's a lot going on. And the really secret ingredient here is, well, how does this transformation happen? Well, it happens by differentiating the formula, differentiation like you learned in high school. So I've color-coded these things to correspond to a differentiation rule that you may remember from math. And the funny correspondence here is in logic, often plus corresponds to or, and multiplication corresponds to and that also holds true here, and it extends to differentiation. So when we apply differentiation rules, we go by these operators. So in this case, we're differentiating like start plus reaches and step, and the color codes sort of correspond to the math at the bottom, where if you have a constant b plus a variable function f multiplied by a constant a, then the way you differentiate it is you differentiate f and multiply on the constant a, and that corresponds to what we saw in the transformation here. Things are not always this simple, so the next thing to show here is, well, what if there's more going on? What if there is something variable on both sides of the and? Well, then we have the product rule that you may also remember from high school to differentiate f times g. Then you differentiate f and multiply that with the undifferentiated g, and then you add f multiplied with the differentiated g. And this just straight applies to logic as well, it turns out. And then there are a bunch more rules for things like negation that don't have a direct correspondence in math. But the real point here is you can you can always do this if you write your Taint tracking, your libraries, your static analysis in another programming language. You can do these transformations yourselves, but they're really hard to get right. Like, likely you will either miss something and you will be missing some results, or you will do some redundant computation. So when we can write it in this declarative language, then everything is handled mechanically for us, including the check that our recursive definition is actually well-formed and has a solution. Okay, so putting all this together in QL, we've written all these libraries for mostly reusable across languages. So what goes into a QL database is essentially the abstract syntax tree of a program. So it's roughly what comes out after parsing. And from that, we can compute the control flow graph. We can put it into single static assignment form, which is very convenient for all sorts of static analysis. And then we can compute things on top of that, like range analysis. And we can resolve virtual dispatch, which is very convenient to find out, like, you have a call to string on object. Where does that go? Well, for that, we need to have tracked types through the program. And then on top of all that, we can build data flow and taint tracking, which is what you saw in the examples, all inside QL. If you should dive into writing QL yourself or something similar, then some surprises you might encounter and might take some getting used to is, well, first of all, everything's computed bottom up. So when we saw the example of the reachability of X, that was not a function that takes in an X and then tells you whether it's reachable. It is rather a predicate that enumerates all the values of X that are reachable. And if that's not your intention, then you have to write it out differently and wrap your head around how to account for that. But computing everything all in parallel, all at once, is also some of what makes CodeQL very efficiently evaluable, and it enables parallelism and enables all sorts of, like, locality and memory management to be automatic. The other surprise is that CodeQL pretty much just has one data structure, and that's the sorted list. That's very different from any other programming language you might be used to, where, of course, you have an unsorted list, maybe just called a list, and you have hash tables, you have sets, and all these things. You don't have that in QL, you just have the sorted list. And it turns out that's really all you need. You can make everything else from that. And in general, if you want to look up a single value in a sorted list, then that takes logarithmic time. But in many cases, when you want to look up all the values from some other list in a sorted list, then that amortizes to constant time. Okay, so this was an introduction to CodeQL. The thing I want to encourage you to do when you get back to your hotel or wherever you go after this day is to hurry up and go and look at the security results for any open source project you might be maintaining, especially if it's something that is exposed directly to the web and to potentially malicious people. So you can enable code scanning in GitHub. That gives you CodeQL for free on open source. If you see results in other people's code, then you can also contribute by understanding the issues, triaging them, fixing them. And if you want to go deeper, there are resources for learning CodeQL, and you'll also find that all of the standard queries, including the ones where I showed you the output, they are all open source, and you can find them in the repository that you see here. So that's what I want to say. I guess also there's lunch in a bit, so if you should happen to talk to me at lunch, then you can ask me about the anecdote of how CodeQL found bugs in the Curiosity rover while it was on its way to Mars, or maybe ask me how it worked out when we once tried to write a whole web application entirely in QL. Thanks, everyone.